All right, we'll try 18 again. But I'm not going to rewrite all those vectors. I'm just going to write it in an augmented matrix. Maybe it was hitting that thing. Okay, 18. Let's see. So the augmented matrix is H. So now what I have to do is go down on row 3. This one is okay. And this one is okay. But now, this one, last row, I have to multiply the first one by 2 and combine. So it's 0. 2 times minus 3 is a minus 6. Combined with 8 is 2. 2h. And we're adding. So it's a minus 3 plus 2h. And let's see. For what values of h is y in the plane? So what we got to do is we got to get rid of that 2 in that last row. I'm going to multiply minus 2 times the second row and combine it down. Minus 2 times minus 5 is a plus 10. Added down makes it 7 plus 2h. Now, in order for that to have values, that 7 plus 2h must be what? Must equal 0. 2h because the h up here, that can be anything, right? But this value right here has got to be 0. So, any questions on that? I'm gonna look at the next section, 1.4. Here it's going to talk about a matrix equation. And the definition there says if A is a m by n, m rows, n column matrix with columns A1, A through n. So you see it's the m cross m is m rows, n columns. And if x is in the Rn, then the product A and x denotes A times X, the linear combinations of the rows of A using the corresponding entries in X. So then it makes it, you see it makes it a linear combination of X1. The X's are the weights on the A. And if you notice the example underneath there, you see that they're having that matrices, and it has the second matrix is the weights for the first vectors. Now on the next page, there's an important theorem there. That theorem 3. It says if A is an m by n matrix with columns A through n, A1 through n, and if B is in there, so then if B is in that span of those vectors, then AX equals B. Then it says has the same solution as the vector equation, x1, a1, so on. And then which in turn has the same solution set as a system of linear equations with augmented matrix. So this theorem is just saying that if you just have that matrix equation, it's the same as the vector equation, which is the same thing as the augmented matrix. And then you can use those things interchangeably. You can either write it as a augmented matrix, you can write it as a linear equation of vectors, or you can write it as a matrix equation. So it's not a proven theorem. We don't have to worry about the proof. We just worry about the application. And the application makes it really nice, because if we have any of those, we can use the augmented matrix to solve it, or if we have an augmented matrix, we can write it in any of those other forms. So you can go interchangeably. That's the nice thing about that theorem right there. Notice it's telling you that theorem 3 right underneath there. The second line says because a system of linear equations may now be viewed in 3 different but equivalent ways. So if you have one way, you can represent it in any of the other ways, whichever way is convenient for you to solve the problem. That's a pretty powerful theorem. It's one that we'll use. And then on top of the page, next page, it's saying the equation AX equal B has a solution if and only if B is a linear combination of the columns of A. So in that theorem, the first has a solution if the second part of that theorem exists. And then the theorem at the bottom of the page is saying, let A be an m by n matrix, then the following statements are logically equivalent. That is, for particular A, either they are all true statements or they are all false. So first one says if B is in Rn, so if B is in that span, then AX equals B has a solution. So if B is in Rm, is a linear combination of the columns of A. Columns of A span Rm, and A is it has a pivot position in every row. So your augmented matrix exists. Then they're going to talk about computing on the next page, computing the AX. And notice that their examples are showing you that you take each row of A times the column of the X's, and you get a row of equation. Okay. 39 is just telling you that if you have an A times the sum of two vectors, then you can do A times the one vector plus A times the other. So that's telling you that this is distributive. That matrix set is distributive. Now, in mathematics, not everything follows a distributive property, but matrices over vectors is distributive. And then the next one is commutative property. So if you have a matrix and you have you have a scalar times a vector, you can take the scalar out and do your matrix vector operations and then multiply the scalar times it. So that's commutative. And that property then, and if this is equal, then you can do it both ways. You know, you can factor a vector out of a product, for that's with A on that theorem, or you can put it in. You can commute those things around. I'm going to back up. Property B is associative property, not commutative property. You cannot commute vectors. You can't interchange them. But you can associate. That's because your multiplication operations, you have to have the same number of columns in the first vector as you have rows in the second to do your multiplication. If you have an A times X, if this is an M, I said M and I put X. If this matrix is an M by N, then this matrix must be an N by, you could do an N by whatever, but it's a vector, it's got to be an N by 1. These two have got to be the same. This has got to match. You see, if you did this, if you did X, A, then you would have an N by 1, and you'd be trying to multiply it by M by N. So you wouldn't have enough rows to match the columns. You wouldn't have enough columns to match the rows. This one, you got enough columns to match each row for this one. And that's what these two have got to be undo. These two have got to be the same. Right? So therefore, you can't commute, but you can associate a scalar when a scalar's in there. And that's why you can, when you're adding things, you can commute in addition, but you cannot commute in multiplication. You know, we're used to, in mathematics, we commute and we associate and we distribute and do all of that, right? Well, this algebra, linear algebra, you cannot do commute. You cannot commute. Okay. Okay, I guess that's there. So for exercises 1-4, it says compute the products in exercises 1-4 using A, the definition in example 1, and B, the row vector rule for computing AX. So if you look back in your example 1, they're just saying that 2 you can't do that one because this is a 1 by no, a 3 by 1, 3 rows, and this is a 2 row by 1 column. These aren't the same. You can't do it. Four, could we do that? So we got a 8, 5, a 3, 1, 1, 1, 1. So we got 2 rows, 3 columns, and we got 3 rows, 1 column. So these are the same, so we can do it. And we're going to get a 2 row, 1 column result. And then the weights are going to be this top 1 times this vector. So it's 1 times 85 plus 1 times 3, 1 plus 1 times minus 4, 2. So that we can calculate. Next problem set. So what we want to do, it's saying to write it as a vector equation. Seven, 2, 9, 3, minus 3, 6, 2. This is a 2 minus 2 minus 5 equals 1. So what we're going to do here is we're going to do a minus 2 times the first column. That would give me the vector. and then a minus 5, second column. Is equal to 1 minus 9, 12, n. So now what we have is the vector. So we've written it in vector form. And then the second matrices is the weights on the vectors. And then it says, or vice versa. So the 8 would be writing it from AX form, writing the vector equation back to AX form. See, this is in, this one here is in vector form. So if we do 8, we'll write it back in AX form. A equals B. And that's what we want to go to. So this is going to be Z1. Z1 times the vector 4, 2 plus Z2 times minus 4, 5 plus Z3 minus 5, 4, 3, 0. So now the A matrix is going to be 4, 2, minus 4, 5, minus 5 and 4, and 3 and 0. And then Z1, Z2, Z4 equals 4, 15. And that would be AX, in this case it's AZ equals B. And what we've just done is we're just utilizing theorem 3, where it says you can write, if it's written one way, you can write it another way, right? That's all you're doing in that particular setup. Okay. The next 9 and 10, this will be the last one we do. Is saying, it says in exercise 9 and 10, write the system first in vector equation, then in matrix equation. So it's 8x1 minus x2, 4, 5x1 plus 4x2 So in vector form, it's going to be x1, 8, 5, and 1 plus x2 minus 1, 4, and minus 3 equals 4, 1, and 2. And the AX equals B, it's going to be 8, 5, and 1, minus 1, 4, and minus 3, x1, x2, and x3. Oh, there's no x3. Thank you. With that x3, I couldn't multiply it, could I? 4, 1, and 2. So we've taken the set of equations, wrote it in vector form, and then in the AX equals B form. All right. That's it.